is development of annealing simulation model for the stainless SUS316L alloy fabricated by L-PBF method based on the cantilever distortion experiment and the simulation. And this talk is actually supposed to be given by one of my PhD students, Q.Jin, but because of the visa problem, he is Chinese in nation, so he needs some visa to enter the Germany, and because of the visa problem, he couldn't make to come here. So that's why I'm presenting instead of him, and I studied this very hard in the last 2 days. Maybe I can do my best. And this talk is about the laser powder bed fusion process, which is one big topic of this whole conference. So, I assume that everyone is familiar with this, but here in this talk, especially I would like to emphasize that in some case, the dimensional accuracy matters in some components. For instance, in the impeller, here near the joint to the other component, maybe the dimensional accuracy doesn't matter because we have to machine it anyway for the joint. But for instance, here and here, the dimensional accuracy or the simply shape influences the overall performance. Or this part, for instance, has some joint part at here with the bolt holes and here. And imagine that if the whole part is distorted during the cutting job from the base plate, then if we connect this part here, and then we cannot join this part. So sometimes dimensional accuracy is one critical factor that we should consider. And there's always some residual stress issue in the laser powder bed fusion system. Depending on the three-dimensional shape of our component, we have more or less always has complex residual stress inside our component in the as-built state. This can produce some distortion when we cut the component from the base plate, or in the worst case, in the brittle material, sometimes cracking as well. And there are many studies that to control the residual stress by optimizing the laser pattern or by adjusting the printing parameters such as laser power and so on. But this is basically unavoidable because we are basically depositing hot material on the cold substrate or the previously deposited layer, and this shrink. So there's always strain mismatch, and we have some amount of the residual stress. Maybe we can reduce it, but we cannot completely eliminate it during the process. So if the component is very sensitive to the dimensional error, for instance, like the impeller or the heat exchangers with two joints, then to prevent the distortion, we have to go for the heat treatment normally. So the annealing heat treatment can effectively relieve the residual stress. And when we go up to high temperature for a long time, then we can more efficiently remove the residual stress. But thing is that if we consider the hardness and the yield strength is normally reduced when we increase the heat treatment temperature and make the longer heat treatment time. So there will be some kind of optimum condition that we do have some small enough amount of the residual stress that we don't have any distortion problem, but we keep the required hardness and the yield strength. That's why we saw that it would be very good to have some kind of predictive model for the evolution of the residual stress, depending on the three-dimensional geometry of the component. And this was the goal of this talk or this research in general. And we started this work first for the very common material of 316L stainless steel fabricated by the powder bed fusion. And material was 316L, and we have used different laser parameters with the Japanese Sodic laser system, which is a replication of the concept laser M2. So the specifications are more or less the same. And we didn't change actually for this research the parameters. We just used all parameters that are recommended by the manufacturer of the machine. And to develop or simply to measure the residual stress, we have to first find out the efficient way to experimentally measure the residual stress. That's why we designed a special structure, which we call cantilever, which is quite common in measuring the residual stress. So we have some cantilever beam in the above, which is connected with the supporter legs. And while we are printing those supporter legs, they are free to move in the lateral direction. So they don't have any residual stress in this direction. But as soon as we print the first layer, then the second layer will shrink, and then there will be some force balance between first and second layer, and again and again. And finally, we have developed a complex residual stress. And afterward, when we cut, then there will be some distortion of the cantilever. And by calculating the residual stress and calibrating the model with this distortion, then we can figure out how much residual stress it is. And for the better calibration, we have used 3 different thicknesses of the cantilever, and we have actually modulated this for the easy heat treatment. So one module has 3 different cantilevers with 3 different thicknesses, and we put in the oven, heat treatment, and then we cut. Then we get all the information of 3 cantilevers with the 3 different thicknesses. This is our model, basic model, and I will not go into all the details of this, but basically this works like this. This is finite element model, the structural analysis, and firstly, we deactivate all the important part by considering the material as do not have any or near zero stiffness. So it's basically some kind of liquid. And then we activate material 1 layer by 1 layer. And then we artificially shrink by the defined amount of the material. So that is kind of the replication of the process, but we average or consider the material is being deposited 1 layer by 1 layer, and then it's shrinking again and again, something like that. So this is not special, it's already published research in the literature, but what was special was that to consider the annealing process, we have used cream material model. So we have used 2 very popular cream material model of time hardening and strain hardening model, having 4 different creep parameters, but one, the creep hardening depends mostly on the creep time, and this one is on the creep strain. So that is the only difference. So from now on is research and discussion, and here is actually our cantilever after cutting the legs. So you can see the distortion while cutting the legs, and here the graph we have number of legs cut on the x-axis, and on y-axis is depth deformation. So we are basically cutting the legs and measuring the deformation of this part to upward, and then we plot here. As we can see, when the annealing temperature was 650 degrees C, then as in the edge-built state, we have a large amount of the distortion. And with increasing the heat treatment time, that's as expected, the distortion is decreasing because of the annealing effect. And when we increase the annealing temperature to 750 degrees C, the annihilation effect is more pronounced. That is also as expected. But one interesting point here, as the material scientist, is that here we cannot eliminate completely the residual stress at this temperature, because I don't put any microstructure, but when we are looking at the microstructure, then here in this temperature for this material is basically we are doing some dislocation climbing only. So rearrangement of the dislocation, so we cannot completely remove the residual stress, although here we have some diffusion. So here we plot the final distortion after cutting all the legs and do the comparison. So in the x-axis we have annealing time and y-axis we have deformation. And here the closed symbol represent the heat treatment temperature of 650 degrees C, and the open symbol is for the 750 degrees C. What we could see from the previous slide, depending on the annealing time and temperature, the final distortion decrease. That means the residual stress is decreasing as expected. And another thing is that the deformation also depends on the thickness of the cantilever. That's of course because the thicker the cantilever beam is, then it's more steeper. So it's difficult to bend. Anyway, our model works like this, basically. So this first calculate the original residual stress while we are depositing, and then it looks all the same actually, but with different amount of stress with the annealing condition. But then when we cut, as in the experiment, it shows the distortion. And when we compare it and calibrate the model parameters to figure out how the simulation model can show the amount of the deformation that we have shown, that is shown by the experiment, then we have the calibrated model. So with many experimental parameters, we could successfully have the fitted parameters. Here is the experimental deformation for selected points. And here is the fitted model. We can see that here and here, those are the corresponding simulation results, and the results are very well represented. And this is the overall figure of the comparison between the experimental distortion and the one with the calibrated time hardening creep model and the strain hardening creep model. As you can see, for different annealing parameters, in overall, the simulation model agrees very well with the experimental data. And another thing is that for this particular material of 316L stainless steel, strain hardening model is slightly better than the time hardening model. Maybe that depends on the material, I think. And when we calculated the error, and when we compare it to all deformation, the error bar was something like 5%. And then we checked the validity of our developed predictive model. So we wanted to figure out whether if our model can be really used to predict the deformation of the annealing structure with complex three-dimensional shape. We have designed two different special structures. One has the auxetic shape with the supporter structure, and one is propeller with supporter structure. And this is the final result. So this is the auxetic structure without and with the annealing heat treatment, and this is simulation. This represents very well the deformation behavior quantitatively, and here is the deformation of the propeller shape in the edgeability condition and annealing condition, and this is actually the experimentally measured deformation by the 3D scanner, and here is the predictive model, and we can see that the distortion is very well agreed. And this is quantitative comparison between the experiment and the simulation for the distortion at here and here. And in overall, there is good agreement, but it's at just 1 point for not for the heat treatment, but for the edgeability state, which is, I think, because this structure was probably too thick. So before we cut the supporting structure, maybe this was a little bit bended, I think. It's at this point, in overall, there was good agreement. So in summarization, finite element model was developed to predict the evolution of residual stress in the during the different annealing condition, and the changes of the residual stress has been predicted by the CRIM model, which has been calibrated by the experimental data. So to validate the developed model, we produced two different complex 3D structures, and seems that our developed model works very well. This is the end of my presentation. Thank you very much.